All right, so here's well, I just did a live demo with this one, right? So Newton's cradle. So there's definitely some collisions going on. So that's going to involve this new collision physics, which has something to do with momentum, mass times velocity, but also has something to do with momentum conservation, the fact that mass times velocity is conserved. Right? But also, the collision that you're looking at is actually a very special kind of collision. It's like a super bouncy collision. So you could quantify this as like coefficient of restitution as 1.0. That's the way to say perfectly bouncy. Okay. But not only is momentum conserved in the system, but also kinetic energy. Now, you guys remember from the last couple of weeks that energy in general is conserved in a closed system or in the universe. Okay? But energy can take different forms. And one of those forms is energy in motion and kinetic energy. And if you have something that's perfectly bouncy, then the physics of that is that not only is momentum conserved, but kinetic energy is also conserved. Right? So hang tight for that. Probably by the end of class today, I might just get to start talking about inelastic collisions. But so we'll begin that. Let's look at this one here. So this one goes by real fast. Okay. You guys know if you drop a ball from some height, say if you focus on that tennis ball, you guys see a tennis ball right there. If you drop the tennis ball from that height, it could only bounce up to that height at a maximum. It's probably going to be a little bit short of that. That would be true, right? Okay. So one of the labs I'm going to have you guys do is going to be basically that. You're just going to bounce the ball off the floor and measure heights, right? And then crunch those numbers a certain way, right? But right, if you throw the basketball underneath this, well, let's check this out. Bam. Right. Now the tennis ball flies off screen, so you can't tell exactly, but it definitely flew up higher than it started. You see that? Right. Now, I guess you could say that maybe some like energy was transferred from the basketball to the tennis ball, but a better way to think about this is that there was momentum that was transferred from the basketball to the tennis ball. Right. Hope you saw that because there was some collision that happened at the point of the floor. Okay. In fact, if you just dropped the basketball by itself, maybe it would rebound to some height. But do you guys see how does the basketball even show up the rebound? No, the rebound doesn't even show up because probably a lot of momentum was transferred into the tennis ball. We can do kind of an extension on this. So look, there's an extra ball up here. I don't know if that's a ping pong ball or a golf ball. It's one or the other, but pow, definitely flies way off screen. And so you got that. A really classic momentum question is this setup here. This is called a ballistic pendulum. Okay, so we definitely won't get to this today, but hopefully the next couple of weeks, you guys can see this at some point. You guys see a bullet was fired into the block, and then the block is on the pendulum, so it swings up to some height. Is that bam, and then swings to some height? Actually, the second part of that is something that you guys saw over the last couple of weeks, okay? In reverse. You guys remember like either a guy or I think you guys had a book problem that said like a chimpanzee like swings on a vine, something like that. If you know the length of the vine and you know the starting angle, you can figure out how fast it was going at the bottom. Well, this is kind of reverse that. Like once the bullet embeds itself in the block, it swings at some speed and therefore goes up to some height. So you can figure out right like how fast was the post collision speed, right? Okay. But the point of a ballistic pendulum would be to answer the question, well, how fast was the bullet fired? And as long as you know the mass of the block and the mass of the bullet, there's enough information that you can solve that. If you know the mass of the bullet, the mass of the block, and how high the swings up to, there's enough information there that you can solve for the initial firing speed of the bullet. But you need to apply the stuff that you're about to learn over the next couple of days, which involves conservation of momentum, because there's a collision. There's a collision between the bullet and the block. In fact, it'd be a perfectly inelastic collision, wouldn't it? Because they stick together. Guess that? And so that's coming up. All right, Magic School Bus time. Magic School Bus. So, it's my, no, not frozen. Why isn't this video playing? All right, here we go. All right, so did I show this to you guys before? This video clip? Yeah, you guys seen this? All right, so they were on a frictionless field. Like one inside a textbook. They're on the there they are. So they're inside a textbook. They're on a frictionless baseball field. So got some really nice physics going on, right? In fact, if it's frictionless, once they're just in motion, like sliding around, they just just Newton's laws take over, and they're just going to be sliding around, right? So yeah, you need a crane to like put them in place because you can't just like walk to some place and like stand in place because you need friction to like speed up and slow down as you're walking. Right? All right, so we got them all set in place, and ooh, can you see how they're having trouble maintaining balance? That would also be true, right? Like if you guys ever gone ice skating, right? Low friction environment, really hard to maintain balance. But what's going to be applicable to what we're about to do today is when this pitcher throws this baseball. So Wanda throws this ball towards Ralphie and whoa, gets kicked backward. Now pause for a moment here because she throws the ball forward, she gets kicked backward. Immediately that reminds me a lot of which Newton's law of motion. Probably all of them kind of apply in a certain way. I'm thinking immediately the third one is like the equal and opposite rule, right? For every force, there's an equal and opposite reactive force, right? So she puts a force on the baseball forward, and the baseball puts a force on her backward, right? So she's going to kick back towards second base. Now you can definitely apply Newton's second law of motion here too, if you want to answer a question like something to do with like the accelerations during the throwing, which happen for a tiny fraction of a second. And then what if you ask the question, what is her like post throwing speed back towards second base, right? Because again, she has a mass, the baseball has a mass, and she threw the baseball at some speed. So the baseball has, it should really say some forward velocity towards the plate that the baseball does, right? There's enough information there that you could solve for how fast she's going back towards second base. Now, the old way of solving it, the really complicated way, there's a much easier way you guys are about to learn today, right? But the old way would say, well, during the throwing motion, there was a force on the baseball and an equal and opposite force back on her. So if you knew what that force was, if you could somehow figure it out, which would be a whole complication in itself, but let's say you figure that out, right? Then that force only acts for a tiny fraction of a second, right? Then you can calculate, well, what is the final velocity of the baseball, based on, so that's a combination of dynamics and kinematics, right? And then you can apply that equal and opposite force to her and divide by her mass and get the acceleration of her, and then go through some kinematic motion and figure out what is her velocity back towards second base. Okay? So yeah, it can be done that way, but a much faster way is to just apply a conservation of momentum, which is just mass times velocity. Mass times velocity of baseball forward is equal to mass times velocity of her going back towards second base. So that's one of the problems that we're going to solve later today. Right, so let me switch my screen back over here. All right, let's solve some physics.